Thank you. Wow, to listen to the list of former folks that have been honored with this is really humbling. So I think the introduction, you know, you just hang around to do things, you hang around long enough and you can accumulate a good list. So I really appreciate being here back in Big Ten land. So I'm a Hoosier by birth and where I was raised, and so I'm appreciate being back in the Midwest and back in Big Ten land here. So, and to talk about a topic which is one of my favorites, that is the topic of water, both the challenges but also the solutions, and we have both. So I'm going to start off by trying to get you to think a little bit now, think about the past and the future. I'm not going to read through all these things, but as you see, we no longer live in the second half of the 20th century, and I say that because there's a tendency for many of us, especially those of us that our hair is not quite as dark as it used to be, to really think about the world and to behave as if we were in our world that was the second half of the 20th century. But what's very important for water, as it really is for, I mean, every engineer, especially every civil engineer, should be thinking not about today or tomorrow, but think about short term as the middle of this century. Because the things that we're doing, the things that we're putting in place, can last 50 years at least, 100 years. So, especially civil engineers, for us, the near term is 2050. So that's the thought process that we need to have here, and that's really the purpose of this slide, is to get you to think a little bit along those lines. And this is changing, so this is an example that I think shows that's reflective of the increasing resource scarcity that we have. But what you see here is the price of a number of materials, and you can see the list of things which are here. It's interesting, if you extended this back 100 years, even in dollars adjusted for inflation, the prices of almost every material have gone down for 100 years, up until right in here. Now you see what's happening. So, you know, we're going from a period of relative stability in many ways. I mean, you look at the turmoil of the last century, you say, how is that stable? But look at the change that we're embarking on here now as engineers, when we try to figure out the best for 2050. The truth is, we're faced with this kind of uncertainty. So you really need a different thought process about what is going to be reliable, what is going to be robust in response to a very changing and pretty unpredictable future. So in response to that, I believe, and many of my colleagues believe, that we are in the midst of one of the most significant transitions in the history of the water profession. Those of you young folks that are embarking on this profession, you're going to have a great time. This is a time of amazing changes, and this table is really meant to contrast some of those. If you start looking at some of these, you see the word integrated and hybrid and integrated and integrated. Water itself, which we have tended to look at in its components, needs to be managed in an integrated fashion. And water management needs to be better than ever integrated into society itself. So as engineers, we need to be able to think in detail, but we need to be able to think broadly at the same time. And the optimization function. We've tended to look at what solutions provide the most economy of scale, because capital was scarce. I think I put this previous slide to illustrate that things like water and energy and materials and labor, they're going to be the scarcest commodity. So how we think about what is the best solution. And we're actually seeing this today in terms of the solutions that are being applied. Many people ask, what's the, what does this cost? That's the infrastructure cost paradigm. What's the value is looking at the fact that there's a transition in terms of what we need to be, what our optimization function is. Time of tremendous change. So having said that, let me get into some of the issues here. And the first thing is we need to know what we need to do. There's a lot that we need to do in detail, but I can boil it down to 3 principal outcomes that we in the water profession need to achieve. And I'm going to go through those with you. So the first is we have, and this is about us and how we have to change. We as the profession have to fundamentally change our approach to water management, because doing what we're doing, we're on the path for water stress and lack of water availability to be the norm on this planet. It is absolutely and totally avoidable because there is enough water, but we have to manage it differently. So what you see here are some of the factors. I'm going to talk about how we do this, and the answer is in terms of integration and integrated solutions. Here's the factors, but we're on the track, if we just let things go, to half or more of the citizens of planet Earth. This diagram it's some fairly old work, but it shows the effect of climate change on the top, which is what everyone talks about. But if you look at the middle is the effect of population and economic growth, and then the combined effects. And of course, red is bad, blue is good. There's an awful lot of red. But it's up to us to change this. That's the first thing we need to do. We need to, and I'll talk about reinventing our profession towards the end of this discussion. Secondly, water management must become much more resource efficient to sustain us into the future. This is now some fairly well-known work by an international group of environmental scientists looking at where we have crossed planetary boundaries. You can see some places we're way beyond the boundaries. I've listed them there. Every one of these actually deals with water. Well, you can see, well, nitrogen and phosphorus, yeah, there's but biodiversity? Well, that's driven a lot. There are many places where we just take too much water out of the environment. And what we put back in just isn't good enough to preserve it anymore. Resource efficiency, because resources are becoming scarce. Water, but other resources. The third thing is not so applicable here in the US, but very applicable around the planet. It's achieving the human right to water and sanitation for all. It's a commitment made by governments through the United Nations. And the facts that we hear all the time dramatically understate this. Fortunately, people are starting to talk about this in more accurate terms. Some specific data here, but let me give you the bottom line. For water, it's not 1 billion people that lack safe water. It's half of the human population. It's less than 1 billion that lack an improved water supply. A little trick of the words. But it's half that lack safe water. And in terms of the word sanitation means whether people have toilets. 2.6 billion people lack toilets. Between 3 out of 4 and 4 out of 5 actually lack appropriate waste management. So if you're in business, this is good news. There's big business out there to do. For the profession, it means we've got a big job and we need to go do it. So here's a way to think about in simple fashion what we need to do. So the drivers, so don't worry, you don't need a computer to do this math. This is the most complicated equation you're going to see, but the drivers, which we could talk about in more detail, but water stress, resource consumption, nutrient dispersal. But also, in our profession, we haven't supported our institutions that deliver these services well enough. And this is in the role I have with the International Water Association. This is really, in many ways, crystallizing the things that we're working on. So what do we need to do? We need to reduce the amount of water that we take out of the environment. Not necessarily that we use. We can reuse it many times, just like Mother Nature. Mother Nature, we all learned someplace that water gets recycled, right? There's no new water on this planet. We need to help and reduce the net out of the environment by at least half and to about a third, to be energy neutral to positive in terms of the water cycle, and recover materials like nutrients. And we have to work on the social and institutional side in terms of strengthening the institutions that actually do this work. We can do all these things. We can do all these things today. We'll do them better tomorrow with the research and the learning, but we can do these things today. So there you go, 3 things. Telephone numbers start with digit, 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 right? It's because people can remember 3 things, right? These are the 3 things we need to remember. So let's get into a little bit the how. So 2 steps. I'm going to go through 2 pieces here. The first is to consider, in a given instance, all of the options that are available for us, and to select the ones that apply in each case. So this could be an entire lecture in itself. I'm just going to give you a couple of things to think about. But the first is to look at the components of the integrated urban and water and resource management system. And you're reading through this list. I'm not going to recite it to you, but look at how broad, look at how diverse that is. There's a tendency in the past to pick 1 or 2 of these and to not even think about the others. So the first is to understand the toolkit. I call this the toolkit for solving our water management problems. And some of these we kind of forget. Let me just give you a couple that we forget about, which are very simple. So I'm going to show you some graphs that are very simple mathematics. One is looking at how much water falls on an urban area, and if we captured it, what it could do for us. So what you see is rainfall captured, some dry areas. So where I live, the rainfall would be about this. This area might be more in this range. And these are population densities then. And I don't know, Detroit might be somewhere in this range. The really dense cities in Asia are in this range. But you know, for people, you need about 100 to 150 liters per capita per day. So you can see that if I drew that line, all the water that many urban areas needs falls right on it. Why haven't we captured it? Is because cities were dirty. They're less dirty and today, so the water that's there is less dirty. In fact, the water that we take out of our rivers is pretty dirty today too. So we just don't think about it. We don't think about the resource that's there. We're used to doing something different. We don't think. Energy. Here is the heat that's available in the used water stream, or in any water stream, but especially the used water stream. And again, I'm looking at, depending on what the water use is, this is the amount of energy that can be accomplished, or that's available for just 1 degree centigrade. Now you can actually extract a lot more than 1 degree out of a used water stream. Wastewater treatment per person takes about 5 to 6 watts. 5 to 6 watts. So you start looking, and this starts to get pretty, this could be a real contribution, right? So maybe it's difficult to get everything that you need, but it's in the ballpark to really contribute. You know where it comes from, right? Is anyone here, the last time you took a shower, did you take a cold shower? The amount of energy that you used taking that shower was about 10 times the amount of energy to process all of your wastewater for that day. Big energy use is actually on the, on the household side, not on the processing side. And source separation. Source separation, separating out. This is the distribution of organic matter, which is chemical energy, and nutrients. If we separate out the gray is the gray water, which is actually about half or 2/3 of the volume. You can see it's relatively uncontaminated, so separately collecting, treating the gray water doesn't take much energy and chemicals because it's not very contaminated. The chemical energy is in the black water, the feces and kitchen waste. The nutrients are in the urine. So it's interesting technologies. Here's one of the enabling technologies. It's the urine diverting toilet. So which is being used in some places. So you just got to think a little differently. So consider all the options and select the best ones for each case. Now, the pieces are half of the story, but the other half of it is taking the proper options for each case must be combined into integrated systems which capture some inherent synergies. Now, here is an example that shows the distribution of energy. This is work from EPRI, so it's generic, but it's based on it's based on real life. The point is that water distribution, in many instances, is actually the biggest, just pumping water. So if we pump water shorter distances, we can save a lot of energy. If you look at reuse, but you save pumping, you can more than pay for fairly sophisticated reuse. So, and integrated systems, taking the toolkit that I showed you a few slides before and deploying it both in centralized, so large centralized, but also in distributed to decentralized components. And all I've done here is take some of these components, the specific technologies, and show you that in some instances, centralized is the best approach, at least with today's technology, but more decentralized systems. And when we look at managing rainwater, something like this green and gray infrastructure. I hate those two terms because one tends to be, who would want gray? Everyone wants green. They're kind of prejudicial, but that's what everybody uses. Distributed along with traditional rainwater management, some basic civil engineering, right? But starting to bring in some really interesting science in terms of how the hydraulically these distributed systems work, and biologically and chemically how they work to improve water quality. This is an area of reasonably active research, but we really need to know a lot more about that. And from a systems component, how do we integrate this distributed component along with the larger conveyance component? Because we know that these systems can't handle the big storms. An integrated system, a really interesting, really an interesting topic again. So, just to give you a picture of, no urban area has all these things put together, but separating potable and non-potable. Potable is only about 1/3 of the water, 1/4 of the water. Separating those, because then rainwater, reclaimed water from, I'm missing one of my builds. There it goes. Reclaimed water from the used water, separating out the black water and yellow water for recovery, even to the point where you can, and there are places that actually have to export salt out of these systems because they're using the water almost to extinction. Very, very water efficient. Everything here is done someplace, even the heat extraction. Nothing that we can't do today. Tomorrow we'll be able to do it better, but we can do all these things today. So one of my examples, just quickly, New York City. So this is Manhattan from the west side, from the Hudson River. The Solaire. This is where water resources are managed on site to mimic natural conditions. You see the green roof, and a view that you need when you look at a system like this is to look at developing the water balance, looking at the hydrology of the system. This has been in place for 10 years, very successful. The wastewater is collected and treated in the basement. Membrane bioreactor in the back reduces the water consumption by 50% and the wastewater generation by 60%. And this doesn't go as far as the newer developments. This is how that one success has led to other successes, because actually these buildings they sell for more. They have a higher property value. So we don't often think about the cost, but not the value of what we do. So just an example. We do these systems, they've got a lot of advantages. Not just cost, but many, many other advantages. And that's what this slide is really doing, is listing a few of those advantages. So we have to take the proper options for each case and combined into integrated systems which capture the inherent synergies. Interesting for practice, interesting for research to get better and better at doing these things. The water cycle, I'll do this real quickly, but the water cycle is increasingly being viewed as a source of resources. So we can recover water in many ways. This is an example of taking a treated effluent and turning it into better than potable water. A lot of other ways, though, to capture and recycle water. Many of them done in this country, even in places that one would think is having plenty of water. And energy and nutrients recovered in a wide variety of ways in treatment facilities. This is just really to give you an overall view of the large number of opportunities. One which is near and dear to a few folks here, but anaerobic treatment of sewage, which is a common practice in South America, especially in Brazil. It's interesting how things develop in one place and are found to be good ideas but don't translate. And I'll come to the social side of this. And things like phosphorus recovery. This is at Durham, Oregon, a struvite precipitation reactor which is recovering phosphorus out of the wastewater treatment plant there. Much going on in this area. And this is part of this being much more resource efficient. Not only inherent efficiencies, but recovering materials out of the water cycle. So the water cycle is increasingly being viewed as a source of resources. As I said, we're in the midst of a transition. And transitions are not just technological in nature, they're social also. People have to change their behavior, both the people that we serve as the utilities, we as professionals, and some of you will go in that, and you as researchers, but even we as practitioners and researchers, we need to understand the different systems and be putting those systems in place and researching those systems. So change is a social, cultural, and political process, and it must be addressed as such. I hate to tell you that education by itself changes little behavior. It changes little behavior. Knowledge can help you understand the things that you need to do to change behavior. So I just want to hit a few of these to make this point. So this is the first, if you're looking to change behavior, the first thing you need to, the first piece of social science that you need is the S-curve of adoption of anything new. Any new idea, any new practice, any new technology. It follows this classic curve. We've actually known this because of the work by the sociologists since the late 1950s. Now, from a practical perspective, it's important to understand that you have different kinds of people with different motivations through this, as this progresses. So just having a good idea and talking to a bunch of folks will actually do you a little good. What you need to do is to find the folks that are the most receptive to these ideas and start working with them. When I say find the folks, it's certain organizations, and it's even people in those organizations. So this is a very hands-on thing if you want to change behavior. So as I said, I'm a Midwesterner, but you know, I live out west now. So so if I put my cowboy hat and my cowboy boots on for a minute, I say, you know, when we drive the herd to the railhead, you know, 1,000 cattle with a dozen cowboys, we don't direct every cattle. We change the direction of the lead steer. Finding the lead steer is how you get this done. There's been research after research, but that's the practical application, is find the lead steer is how you get things done. And then when you have a new idea, this is a table. There's some really great work in energy that's been done, and this table is really depicting that same sequence, but your new idea first has to get into application. And it may be revolutionary, but people can't envision the revolutionary because too many other things need to change. So your new idea has to first replace something which exists. So, you know, we all have our personal computers and so forth. I see a few sitting there. You know, when the initial, many of you know this, but when the initial market research on portable computers said that, well, this is interesting, but we'll only sell 100 of them because people couldn't envision how they would be used. Every transformational idea, every good idea faces that. So the first thing you have to do is get it out there so that people start experimenting with and learning how they could do new things. But you've got to, so that's part of this process. Once it gets into practice, every new thing goes through a learning curve. Every new thing goes through a learning curve. All of us are learning new things. Many of you are going into the laboratory, and the first time you went into the laboratory, you weren't very good, right? You go through a learning curve. Technologies go through a learning curve. Now, this is an example from energy. And you see that by use, this is not by time, this is by use. It goes through first a quick learning curve, but this goes on forever. So getting things into practice, if it's a good idea, is crucial, because the first time we do it is never the best. We only get to the point where we see the full value when we get out to this area. So if you have a new idea, find those lead steers, get out there, find a place where someone will use it, and then you start running down this curve and you get better and better and better at it. Pretty common sense, isn't it? But that's it. And then different things find different niches. There are a number of things, so there is no perfect answer. Energy again, but different technologies fit different niches, and as they're used, then they go through their curve. Very good work again in the energy area. So change is a social, cultural, and political process, and we have to address it as such. Have to address it that way if you actually want to change the world. Which I know that University of Michigan, you're about educating people to change the world, which is what we as engineers should be doing. So you need to understand this as well. We need a new approach to professional practice. So let me give you a simple example. If the traditional approach, if you need more water, people always think, where can I get more groundwater or surface water? And if we need to expand, our wastewater plant. The first question, and the second, and the third, and the 10th question is, what are the discharge standards? What are the discharge requirements? What if we just ask different questions? What if the first question is, where can we get reused water, and where can we reuse it? We would get different answers. See how biases and changing biases. Risk. I'm going to take a minute here because the first question when there's something new, someone says, well, who's going to take the risk? Who's going to take the risk? You want to take a risk? Nobody wants to take a risk. You should manage it. What I'm showing you here is the standard tool for risk management, which is to identify the risks and the opportunities, get some sense of their likelihood, their impact, but the mitigation. Probability and mitigation. Civil environmental engineering, your construction management folks do this all the time. This is a standard part of civil engineering. What you do then is you can take this, if you got probability and mitigation, you can actually, cost is not a single number, it's actually a probability distribution. You generate this by Monte Carlo analysis. Because what tends to happen is we have a pretty good sense of the midpoint of the developed things, but we get really concerned, so we look at maybe an 80 percentile. See, this doesn't, it's not, I see people do this all the time. So looking at a new thing is to do the risk and opportunity analysis. Now, if you have a risk that can't be mitigated, that's a fatal flaw. An important risk, significant consequences, reasonable probability, that's a fatal flaw. In the absence of that, now look at this. That risk analysis, though, helps you to look at, if you know the things that can go right, that will help you, and the things that can go wrong that will hurt you, you put that into your implementation plan. Successful innovation. It's not by chance, there's actually a methodology. Facilities, also components of facilities and components of our infrastructure have different lives. So actually we should be looking to design our facilities for retrofit. So we have some of the deed and the head and so forth. You think about your buildings, eventually your physical infrastructure, it needs to be rehabbed, right? What if we thought about how to easily rehab our buildings? What if we thought about how to easily adjust our infrastructure? Different way to look at things. And this can be done. Here's an example from my own practice of the layout of a treatment plant for 100 years that's adaptable to different technology. You just have to think about it, then there are answers. So legacy systems. So we've got treatment plants and collections and so forth. So, but we can use things differently. The point of this slide is that we can use things differently as we go forward. We're not stuck using them as we have in the past. Here's one which I sometimes get asked. I stuck this in here. I sometimes get asked what the skills of a professional engineer are. And you're reading through this, and I'll tell you, this is maybe one of the more important ones here, is the emotional intelligence. So again, how do we get these things done? It's the combination of all these skills. You will improve all these skills throughout your entire career. I'm nowhere nowhere near where I want to be here. I'm still working on these things. So, new approach to professional practice. One more point, and it's coming back to the transition. Transitions require leadership. But leadership, it's required to accelerate the change process. But leadership is a learned skill. And this is a whole other lecture. But the point is that there are sources. In fact, I've shown you here the source that I like the most in terms of leadership and how to do it. There's 5 things. It's actually, you can boil it down to be something pretty straightforward. You don't have to be inspirational to be a leader. You just have to have an inspirational message. And tell the message and it'll carry. So us engineers, sometimes we're a little afraid to get up and just have a good message and tell it in a clear, simple fashion. And Kozis and Posner, this is, as you can see, this is in the 4th edition. They've been at this for a long time. What they found is that leaders also have to be credible. So what I'm showing you are the key chapters out of a book that's about this thick. They would often studied credibility, produced another book that's about this thick. That's what they found. To be credible, you have to be honest, forward-looking, inspiring, competent. Who here doesn't want to be that, right? It's simple. Maybe not easy, but it's simple. And you can look at this in a process fashion. This is also some work in terms of, but if you see, here's where we are, there's where we want to be. You start engaging people, you start creating wins and successes, and you move forward and you get there. So leadership is required to accelerate the change process, and I would say it's a learned skill. It's a learned skill. So here's what I've said, and I'd be happy to entertain any questions that you might have. Thanks very much.